Thomas Simpson, who lived only 41 years on earth, made this phenomenal contribution to numerical integration. Why his contribution is important? Because it improves upon the accuracy that the trapezoidal rule gives you and makes it much more workable. So, instead of, so there is a curve, right? The function is, when you draw a function y equal to fx, something like this or this. So, these are curves. So, these are not straight lines. So, straight line approximation is not good. So, approximating this by a straight line, for example, here to here is worse than an approximation that I can make by a curve like this, for example. So, a curve would approximate a curve better than a straight line, just simple dictum. So, what he did, so this is how mathematics progresses from the linear to the quadratic term. So, straight line represents the linear term and then you go to the quadratic term. So, from the straight line you go to the parabola. So, now instead of having an approximation done here through a straight line, the approximation is done using a parabola. So, that was what Simpson's contribution was about, and that is what we are going to really work out. So, again we will start with f is continuous. So, f is from A to B, AB to R. F is continuous and f of x is greater than or equal to 0 for all x in AB. So, again the delta x for reasons of economy in the writing, we will write delta x as h here, the step length, which is again b minus a by n. But here our way of looking at the things would be very different. In the trapezoidal rule, we worked with 2 points y1, y0, y1, y1, y2 at a time. Here we will work with 3 points, right, and that is exactly what I am trying to show you here, that this was the idea, this was Simpson's idea. So, here is this curve. So, for example, it does not matter whichever way you want to draw it, you can put it like this, I am just arbitrarily drawing it A and B. So, here is my x0, here is my xn. So, here is my, so maybe it is this amount, so this is my x1 and then this is my x2, this is my x3 and so on. So, what I do, I consider these 3 points and approximate the curve here by a parabola, because for a parabola of the form ax square plus bx plus c, I can immediately evaluate the integral, because for which my antiderivative is known. This thing cannot be done if I take some arbitrary curve. So, that is why we had approximated by a parabola. So, that is, so here is x0 of course. So, what we have done, we have made an approximation here. So, this is our approximating machinery. So, let us look at take this thing up and make a more closer look. So, here is my A equal to x0 and and this is my x2 with x1 here. So, this length is h and this length is h. So, here is your function, here is a quadratic function. This is actually of the form ax square plus bx plus c. And essentially you want to find the area, this area, you want to find this area. Again you go to the next part and again you fit by that curve and again you compute this area. You might think it is a complicated way, it is slightly complicated way, but it has lesser error. That is what we would find, one would find. Right. If I want to actually find out such an area rather than doing it from x0 to x1, it is much more easier if we look at it in this way. Basically x1 can be considered as a symmetrical point, this could be thought as a negative point, this could be thought as a positive point. So, it is up to you. Basically we are making a translation, basically we are now trying to compute the area, right, we are trying to compute the area of this curve. So, I do not know. So, I am fitting it by ax square plus bx plus c. I do not know what is a, b and c. You can choose a, b and c, but I need not. So, without choosing a, b and c, how can I do it? That is the key idea. With some curve a, b and c are not known to me. So, here is my curve. So, this is the point minus h, this is the point 0 and this is the point h. So, this is okay, right. This so what is this area? So, call this as y1, call y1 or y0. This is y0, this should be y1, this should be y2. So, this is the point minus h y0, 0 y1, h y2. So, let me just try to understand, because every time we are taking a pair of 3 points, here we have x0, x1, x2. So, it could be minus h, 0, h. So, we are trying to understand how to evaluate. So, basically if I evaluate this sort of area under this particular curve, right, and I am going to add up those areas. So, how do I do, knowing what is y0, y1, y2, right, that is the idea. So, the idea here is the following, that I think I should, the curve has to be a bit clearly done. Wait, maybe I have not explained here properly. I will just do the explanation a bit clearly. See what happens, this is the function between x0 and x2 and this is your x1. So, this is your y0, this is your y1, this is your y2. The idea is that you draw a curve which is quadratic and which takes these values. Just a moment. So, or you divide it in such a way so the idea is that the curve ax square, what Simpson said that if you want to estimate it, so you you take the curve ax square plus bx plus c in such a way that the function value at x0, function value at x1, that is at the partition points, coincides with the function value of that quadratic function. So, the value of x0, so ax0 square plus bx0 plus c is actually y1. So, x0 square plus bx0 plus c is equal to y1, while ax1 square plus bx1 plus c is equal to y2 plus ax2 square plus bx2 plus c is equal to y3. So, that is the requirement of, so this is the requirement that Simpson possesses. So, earlier picture was not very clear. So, this is the idea, that this is the way I have to fit in a curve. You may not always be able to do so, that is the whole. So, wherever you can do so, if I assume that I can do so, then what should be these coefficients a, b and c, how they are related to y0, y1, y3. That is the key idea, that I want to draw the curve in such a way that the given point data points x0, x0, y1, x1, y2, x3, y3 are also the points on the curve ax square plus bx plus c. They also lie on the graph of the curve ax square plus bx plus c. So, what should be such a curve? What is your a and b and c? How are they related to y0, y1 or y1, y2, y3, so that this fitting makes sense, this fitting actually happens. So, basically once I have this curve, I am now computing this area under this curve, right. So, this y0, y1, y2, they are the same because they are also lying in this curve. So, here we are now going to evaluate this integral. So, what is this? So, I want you to compute it out. I really don't want to waste my time, not waste my time, I can never say that, but rather waste my energy doing so, which is anyway, if you want I can just do it. It is too elementary not to do it. And then of course, you know what the answer is, you can I am writing down the final answer. The final answer is, I am writing it down from the Thomas's calculus, is so sorry 2h square. So, you put h and then you put minus h and do all sorts of things.
So, there will be 6c then, because 2 times c.
Yeah, right sir, right here, 6c hoga, because h minus h, ch minus ch, ch no minus आ गया ना यहाँ पे, there will be minus.
Then minus of minus h is the
हाँ minus h 2ch, so हाँ 2 अच्छा 3, so 6 आएगा, right. So now how do I relate it to the points y0, y1, y2? See, it does not matter whether I am integrating it from minus x0 to minus I am integrating from x0 to x2, or it does not matter. See, this y0, y1, y2, these values matter. Okay. So, ultimately this whole integral can be represented in terms of y0, y1, y2. So, even if we integrate it from x1 to x2, it does not matter, they ultimately this is the representation. So, how do I do it? So, I know that it passes through the points minus h y0. So, it passing, so this curve is passing through these points 0 y1 and h y2. Now, when you know that, so you know that it passes through minus h0. So, y0 is equal to a h square minus bh plus c, and then you know it passes through 0 y1. So, y1 is equal to, so you put 0, y1 is equal to c. Then you know it passes through h y2. So, y2 equal to h square plus bh plus c. Now, knowing that c is equal to y1, right, if you so from here what I will get? From here I will get ah square plus bh. What is that? Ah square plus, from here, sorry, a square minus bh is equal to y0 minus y1, because c is y1, and from here I will get ah square plus bh. You see, ultimately I have to find ah square and c. That is my goal. Replace it in terms of y0 and y1. So, a square plus bh, it is becoming y2 minus y1. So, if I add these two, I will get simply 2ah square with bh getting cancelled is equal to what? y0 minus y1 plus y2 minus y1. So, it is becoming y0 plus 2 y1, sorry, my y0 minus 2 y1 plus y2. This is what is, so this is my 2ah square. So, let me see. So, my this integral finally it is written in terms of h3. So, I have converted, it does not matter what is your end of the integration. Even if you put x0 to x2, still the same story will come through. Ultimately the same story will come through. That's the clear idea. That is why we did it in this. So, basically these are thought experiments. You translate this whole thing and put it here, where your x0 coincides with minus h1 and x2 coincides with h, x2 coincides with h and x0 coincides with minus h, x1 coincides with 0. So, it makes it look easier. So, you have y0 minus 2y1 plus y2 minus 6 plus 6 y1. Oh, it looks dangerous. So, what is my game? H by 3 to y0 minus 4y1, sorry, plus 4y1 plus y2. So, that is the integration. That is the integration. So, now let us, so if I go to other points, say if I go to the next set of points, which is y2, y3, y4, it will become h by 3 y2 plus 4y3 plus y4. So, that is just, this is a cycling process which goes through. So, because the next set of points would be x2, y2, x3, y3, x4, y4. So, let me just now try to write down the estimate of the integral that this method gives me. So, now you know that, okay, if I go to the next one, you know what would happen. So, I try to make an estimate by the Simpson's rule of this. So, the first one gives me h3 plus y0 plus the first one 4y1 plus y2. The second one will give me h by 3 into y0 plus y2 plus 4y3 plus y4. So, first points are 0, 1, 2, then is 2, 3, 4, then 4, 5, 6 and so on and so forth. And so, the last section, the last part of this dot 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 dot, it continues. The last one would give me h by 3 y n minus 2 plus 4 y n minus 1 plus y n. That is what would happen, the last part. So, if I sum them up, it gives me a very beautiful symmetric thing, because you see y2 lands up twice. Y4 will land up twice. So, all the even ones, even indices will land up twice, while the odd indices will land up 4 times, excepting y0 and yn. So, these are the endpoints. So, it is so this I can now write integral a to b is y0 plus 4y1 plus 2y2 plus 4y3 plus 2y4 plus, if I go on, it will become 2yn minus 2 plus 4yn minus 1 plus yn. It is not the odd and even type. Basically, the two endpoints, the one which has a common endpoint, the y2 is a common endpoint between two such blocks. So, the common endpoints, one will be repeated twice, and obviously the other ones which are in the middle will come, we have the 4 as the coefficient, because that is what we get. You see, the beauty of this, or the power of this, is that you just don't need to know anything about the nature of the quadratic function. You don't need to know what is ABC. That is the key idea, that without knowing that is why Simpson's rule is so important, that without knowing, so I am fitting a curve which has to have some properties, it has to pass through all the points which is given to me, and it can be used for integration, but without really knowing the nature of the curve, the capital A, capital B and capital C, you can actually just use the y0, y1, y2, these the functional values given to you, the x0, y0, these y values given to you to actually evaluate the integral. This is a very, very interesting point which one has to observe. So, let us just take care of this thing. For example, so y is delta x here. For example, let us look into this integral. You know what the real answer is to this integral. This is and what is tan inverse 1? It is pi by 4. So, basically this integral is pi by 4. So, let us see what is the difference between pi by 4 and this integral if we compute them numerically. So, let us use the Simpson's rules. If I use the Simpson's rule, so in the and I use n equal to 4, use n equal to 4, equal to n equal to 4, then you have to evaluate this function at these 4 points. So, I am just taking out the result from, so by Simpson's rule, so n equal to 4 point means what? Between the interval 0 and 1. So, n is 4 means 1 by 4 is again 0, 1 minus 0 by 4. So, this is your h. So, it is 0 to 1/4, 1/4 to half, half to 3/4 and this. So, you have to know the functional values at these points. At 0 of course, you know it is 1, at 1 you know it is half, and then you know that of course, the function value is decreasing. So, at 1/4 you know what is the value, if at half you know what, and compute those values. So, knowing that, you can compute this out and it turns out to be 0.7854. So, approximately this is 0.7854. So, let me use my calculator here in the machine and then let us see what is pi by 4. So, pi by 4 was 3.1415. Okay, let me just do a little division. Just take pi to be 3.14. So, let me me just see the calculator, where the calculator is. So, here is the calculator. So, here is 3.14 divided by 4, it comes out to be 0.785. So, it is amazing match, you see. So, it is almost roughly the match is quite amazing. So, you see Simpson's rule is giving you doing a much better job for you. You see that is why Simpson's rule is important. So, life is important when you really contribute to understanding human knowledge, and this man just lived 41 years, and that's what surprises me, that he could give so many things in. So, we now shut down this game, integration game. So, in the next lecture on sequences, we are going to make a higher jump. We are going to go into what is called advanced calculus or real analysis. We will start talking about sequences, and that I will hardly take, I will not, I can talk it out from many books, but I will just tell in the way I will just go on doing even an extempore lecture on it.